Hello, welcome to this lecture video. So I am teacher Melay, and today we will be discussing topic on linear equation, particularly the application of linear equation to network flow. So it can be network of streets and irrigation network. For this example, we will consider network of streets. But we have to follow this junction rule that the total flow into that junction must equal the total flow out at each of the junctions in the network. So let us consider this example. The rate of flow of the motor riders into a one-way street is shown in the diagram, and the diagram is in the next slide. So in intersection A, the rate of flow is 60, and B and C, the rate of flow are 50 and 10 respectively. Our objective is to find the possible flow along each street. So this is the diagram. So as you can see here, we can see the direction where the riders can pass, just like if they are in A. So they have three options, whether to go to letter B, C, or D. We have arrow towards or pointing towards B, C, and D. So we have here F1, F2, and F3. While for letter D, if you are in letter D, the motor riders can pass through F5 to go to letter D, or they can pass from to D going letter B. Okay, so we are going to use this for us to determine possible equations that can be formulated in such a way that we can use the linear equations. So in the given, it is also indicated that the rate of flow in junction A or intersection A is 60, for B it is 50, and for D it is, or rather for C it is 10. So let us focus our concentration to letter A first. So we can see here that the total flow is 60, and this is equal to, so we have here the flow 1, F1, F2, and F3. So in coming up with equations, we must remember our junction rule that the total flow into junction must always be equal at each of the junction in the network. So let us also focus our concentration to B. So we can see here that all of our arrows is towards B, unlike for A, it is in opposite direction. So which means, so let us write 50 first. So 50, or rather let us write first our equations F1 plus F4 plus F6, and the total is equal to 50. So the flow in and flow out. And then for letter C, let us focus our concentration to intersection C. So line F3, F5 is towards 6, F6 is in opposite direction. So which means F3 plus F5 is equal to 10 plus F6, or F6 plus 10. And then for letter D, so we have a flow F2 towards D, and in opposite direction, we have F5 and F4. So we can actually write this as F2 is equal to F4 plus F6. So using these equations, we can actually come up now with F1 plus F2 plus F3 is equal to 60. F1 plus F4 plus F6 is equal to 50. F3 plus F5 minus F6 is equal to 10. So if you can still recall in our previous slide, this is F6 plus 10. F3 plus F5 is equal to F6 plus 10. But of course, our objective is to place the total flow or the rate of flow only on the one side of our equation. So we transpose it to our another side of the equations, or we just simply added or rather subtracted F6 on both sides of the equation. Similarly, that is also what we do in our fourth equation. So we just transposed F4 and F5, or simply we deduct F4 and F5 to both sides of the equation. So it is now F2 minus F4 minus F5 is equal to 0. So this can be rewritten into a augmented matrix form. So our first column represents our F1, second is F2, third is F3, fourth is F4, 5 is F5, sixth column is F6, and of course the total rate. So we have F1 plus F2 plus F3 plus 0 F4 plus 0 F5 plus 0 F6 is equal to 60. So that is the process, of course, in converting it into augmented matrix form. Now, next, we are going to reduce this. So using the Gaussian elimination method. So we have here, of course, our matrix form and do some operations like, for example, in our first column, our objective is to remove 1 in our second row. So we are going to use our first row because this is 1. So we can do R2 minus R1 to change our second row data. So this is 1 minus 1 is 0. 0 minus 1 is negative 1. 0 minus 1 is negative 1. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 0 is 1. And 50 minus 60 is negative 10. So let us copy this last matrix. So we are already clear with our first column. So 1 for our first cells and 0 for all the rest of the rows. And then next, let's move to our row 2. So our objective is to make negative 1, 1, and to clear the values again. So the row 4 and the row 1. So it's a negative 1, so we are just going to multiply this with negative 1. So we have negative R2. So the opposite sign, negative 1 to positive 1, negative 1 to positive 1, 1 to negative 1, 0 to 0, 1 to negative 1, and negative 10 to 10. So let us move. Okay, so using this last matrix, our objective is to remove 1 in our row 4. So by doing again algebraic operations, so this can be removed by deducting R4 minus R2. So let's, of course, change the entries in our row 4 using these operations. So 0 minus 0 is 0. 1 minus 1 is 0. 0 minus 1 is negative 1. Negative 1 minus a negative 1 is 0. Negative 1 minus 0 is negative 1. 0 minus a negative 1 is positive 1. 0 minus 10 is negative 10. So let's move to the next slide. So using the last matrix, our objective is again to make our first row entry here be equal to, again, 0. So how to do that? We can do R1 minus R2. So it is 1 minus 1. So of course, 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 1 is 0. 0 minus a negative 1 is positive 1. 0 minus 0 is 0. 0 minus a negative 1 is positive 1. 60 minus 10 is 15. So using again our last matrix. So we are already all set again with our second row. Let's move to the third. We are all set with the first two columns. Let's move to the third column. So our objective is again to make -1 in our row 4 be equal to 0. So to do that, we will again do algebraic operations, and that is R4 plus R3. So to do that, so it's a -1 plus the 1, 0, 0 plus 0, -1 plus 1, 1 plus -1. So -10 plus 0, the results are all equal to 0. So this is now our final matrix, because as you can see here, we have 1 and 0 to all the rows, 1 in a second row and 0 to all other rows. Or we already came up with identity matrix. So we cannot, of course, do something anymore with our row number 4. So we can now rewrite this as x sub 1 is equal to 50 minus x sub 4 minus x sub 3, x sub 6. This is our x sub 4. This is our x sub 6 transpose on the other side of the equation. That's why it is a negative x sub 4 and negative x sub 6. Similarly, for x sub 2, we can write it as positive x sub 4 plus a x sub 5 plus, of course, the 0. So we just, of course, transpose this again to add to the other side of the equation. And for x sub 3, it is 10 less x sub 5 plus x sub 6. And for our x sub 4, x sub 5, and x sub 6, because of course we cannot see values here, because it's limited into 4 rows only. Therefore, x sub 4, x sub 5, x sub 6 can be used as parameters. So we have 0 value for x sub 4 in our reduced form. So it also means that it can be used as a parameters. So for 5 and similarly with 5 and 6. So how can we use these equations now? We can actually substitute values in our x sub 1, x sub 4, x sub 5, and x sub 6 for us to come up with values x sub 1, x sub 2, and x sub 3. So using this equation, we can substitute, or we can see all solutions to the systems, or we can give all solutions to the systems. We can show all possible flows, but of course we have to be logical also, that not all possible solutions here may be realistic, or it is not accepted to real life. And then also you have to consider also that we can actually impose here constraints like F1 is greater than 0, F3 is greater than or equal to 0, and F4 plus F6 is less than or equal to 50. So of course, using this, and also F5 minus F6 is less than or equal to 10. So this can still be modified if you want, by using other considerations, or setting other constraints like maximum and minimum flow, or the maximum riders that can pass through one street to another street, and all other possible situations. So this is all for this video. Thank you for watching.